forward DC to DC converter requires a minimum load at the output, because without minimum load, excess output voltage can be produced. So always load should be always connected to the DC to DC converter. Like a chopper, we have to always keep the load, otherwise voltage will be very higher value. So always for choppers, you should always keep the load, otherwise voltage will be very high at the output. So a forward DC to DC converter requires a minimum load at the output, because without minimum load, the excess output voltage can be produced. See, always for a DC to DC converter on the chopper, you always have to keep the minimum load. Otherwise, what is going to happen is the output voltage will be very higher. It is the reason always you have to keep at least a load you have to keep. Otherwise, the voltage will be very higher at the output. So a forward DC to DC converter requires a minimum load at the output, because without minimum load, excess output voltage can be produced. Power electronic converters are extensively used in adjustable speed drives, and power electronic converters produce harmonic distortion. Power electronic converters are extensively used in the adjustable speed drives, and the power electronic converters produce harmonic distortion. I already told you the power electronic converters, they are going to inject the harmonics into the system. So these are basically very used, extensively used in the speed drives. You have to control the speed. So these power electronic converters are extensively used in the speed drives, adjustable speed drives, and these are going to inject the harmonics into the system. A dual converter is used to control the speed and the braking operation of a DC shunt motor in both the directions of rotation. A dual converter is used to control the speed and braking operation of a DC shunt motor in both the directions of rotation. See, dual converter is a 4-corner chopper. So we can say simply that we can control the DC shunt motor in all the directions. Either forward direction or backward direction. We can go for motoring, we can go for regenerating, we can go for even blocking, braking. All these things we can easily control with the help of dual converter. For low speed, high power, reversible operation, the most suitable drives are cycloconverters fed AC drives. For low speed, high power, reversible operation, the most suitable drives are cycloconverter fed AC drives. So for low speed, high power, reversible operation. We are going to use the cycloconverters as the drives. So for low speed and high power reversible operation, the most suitable drives are the cycloconverters fed AC drives. So for low speed, high power reversible operation, the most suitable drives are the cycloconverters fed AC drives. Cycloconverter control has the advantages of smooth low speed operation with regeneration braking and good dynamic response. But it has low speed range, and because it uses large number of thyristors, it becomes economically acceptable only when the drive rating is high. So why these cycloconverters are used for low speed and high power reversible operation? Because the cyclocontrol has the advantages of smooth low speed operation with regeneration braking. Means low speed operation we can easily get with regenerative braking also we can get with the help of cycloconverter, and good dynamic response also we are going to get. But it has low speed range, and because it uses large number of thyristors. So because of using large number of thyristors, we can get only low speed range, and it becomes economically acceptable only when the drive rating is high. So whenever the drive rating is high, we are going to use the cycloconverter to control the low speed range operation. So with the help of this, we are going to get the regenerative braking and also good dynamic response. Cycloconverter control, it is used only when the drive rating is very higher. So therefore we can easily get the good speed range, and the low speed range operation we can get with a regenerative braking and the good dynamic response. Cycloconverter control has the advantages of smooth low speed operation with regeneration braking and good dynamic response, but it has low speed range, and because it uses large number of thyristors, it becomes economically acceptable only when the drive rating is high. So the cycloconverter is going to use basically large number of thyristors, and it is economically acceptable only when the drive rating is high. Then only we are going to use the cycloconverter to control the low speed operation with regenerative braking and good dynamic response. The buck boost converter, the maximum value of the switch utilization factor is 0.75. So this is the point that you have to remember. In buck boost converter, the maximum value of the switch utilization factor is 0.75. So in the buck boost converter, the maximum value of the switch utilization factor is 0.75. So in the buck boost converter, the maximum value of the switch utilization factor is 0.75. So in the buck boost converter, the maximum value of the switch utilization factor is 0.75. DC choppers, the waveforms for input and output voltages are respectively continuous and discontinuous. In DC choppers, the waveforms of input and output voltages are respectively continuous and discontinuous. So you can see clearly, input is a DC, fixed DC, so it is always continuous. Whereas the output, with the help of switching, we are going to make it discontinuous, sometimes non-zero, sometimes zero. So it is called as a discontinuous. So input is always continuous, whereas the output is discontinuous. So in DC choppers, the waveforms for input and output voltages are respectively continuous and discontinuous. For a given output average current in the load of any chopper, the ripple content in it can be reduced by keeping the duty ratio of switching is constant and increase the frequency of switching. For a given output average current in the load of any chopper, the ripple content in it can be reduced by keeping the duty ratio of switching is constant and by increasing the frequency of switching. So if you want to decrease the ripple current in the chopper, then definitely the ripple current is directly proportional to D by F. So keep the duty ratio constant, increase the frequency of switching. So with the help of this, we are going to reduce the ripple content, or the ripple content we are going to reduce. For a given output average current in the load of any chopper, the ripple content in it can be reduced by keeping the duty ratio of switching is constant and by increasing the frequency of switching. So because in any chopper, the delta I is directly proportional to D by F. So delta I means ripple content. So if you want to decrease it, keep the duty ratio constant and increase the frequency of switching, so that the ripple content can be decreased. In a thyristor DC chopper, current commutation results in best performance. In a thyristor DC chopper, current commutation results in best performance. In a chopper, if you are going to use the thyristor, I have already told you in the inverters and choppers we are going to use the fully controlled devices. But in case if you are going to use the thyristor in a DC chopper, then definitely we need to use the force commutation circuit to turn off. So here we are going to use the current commutation, which is going to use in order to turn off the thyristor, which is going to give you the best performance. So in a thyristor DC chopper, current commutation is going to give you the best results. It is current commutation results in best performance. Question: if they gave a single phase inverter, then by default it is a single phase full wave inverter. See, suppose in the question if they gave a single phase inverter, then by default it means a single phase full wave inverter. See, if in a question if you see a word which is a single phase inverter, then by default it means that it is a single phase full wave inverter. When the line commutated converter operates in the inverter mode, then it only delivers the real power to the AC supply. I have already told you, whenever the full converter is going to operate in the inverter mode, then the load is going to deliver only the real power to the AC supply, but not the reactive power. The load is going to deliver only the real power to the supply, but not the reactive power. So whenever the load commutated converter operates in the inverter mode, then the load is going to deliver only the real power to the AC supply, but not the reactive power. The load is going to still accept the real power. It is going to absorb the reactive power. So whenever the fully controlled converter is going to operate in the inverter mode, the load is going to deliver. The load is going to deliver the real power to the AC supply, but not the reactive power. The reactive power is still absorbed by the load. Commutated inverter changes DC voltage to AC voltage. See, a line counted inverter changes DC voltage to AC voltage. See, whenever a fully controlled converter is going to operate as an inverter, it is going to convert a DC voltage to AC voltage. By using one switching in 90 degree, by eliminating higher order harmonics, the fundamental peak value is very, very less. So we eliminate this by using two switching in 90 degree. By using one switching in 90 degree, by eliminating higher order harmonics, the fundamental peak value is very, very less. So we eliminate this by using two switching in 90 degree. So what is going to happen is basically if you are going to increase the switching in 90, if you are going to increase the switchings in 90 degree, then what you are going to happen is basically the lower order harmonics are going to get decreased and the higher order harmonics are going to get increased. Because the peak values of the lower order harmonics are going to get decreased, whereas the peak values of the higher order harmonics are going to get increased. That is the meaning of this one. So by using one switching in 90 degree, by eliminating higher order harmonics, the fundamental peak value is very less. So we eliminate this by using two switching in 90 degree. So whenever we are going to increase the switching, if you are going to increase the switching in 90 degree, then we can say that simply we are going to decrease the peak value of the lower order harmonics we are going to decrease and increase the higher order peak values. So by increasing the switching in 90 degree, we are decreasing the peak values of the lower order harmonics and increasing the peak value of the higher order harmonics. A PWM switching scheme is used with a three-phase inverter to reduce lower order harmonics and increase the higher order harmonics. So a PWM switching scheme is used with a three-phase inverter to reduce the lower order harmonics and increase the higher order harmonics. So with the help of PWM, we can decrease the lower order harmonics and increase the higher order harmonics. Or simply we can say that, with the help of PWM, we can eliminate whatever the frequency we want. Whatever the harmonic frequency we don't want, we can easily eliminate with the help of PWM switching. So with the help of what is going to happen, harmonics are going to get reduced. So we can easily make a filter to filter the remaining harmonics. So we can easily design a filter which can filter the remaining harmonics also. So therefore the filter design will become easier. So with the help of PWM switching, what is going to basically happen is here, we can reduce the harmonics whatever the frequency which we don't want. And also the filter design is going to become easier because some of the harmonics we have already eliminated. And the lower order harmonics are going to get decreased and the higher order harmonics are going to get increased. Peak values. Triangular PWM control when applied to a three-phase. Triangular PWM control when applied to a three-phase BJT based voltage source inverter introduces very higher order harmonics in the voltage on the AC side. Whenever the triangular PWM control when applied to a three-phase BJT based voltage source inverter introduces a very high order harmonics in the voltage on the AC side. So I have already told you, PWM, pulse width modulation, always the reference signal, either it can be sine or it can be square. Whereas the carrier signal, it is always triangular in nature. So therefore, whenever the triangular PWM control scheme, when applied to a three-phase BJT based voltage source inverter, introduces a very higher order harmonics in the voltage side on the AC side. So here, see, I have already told you voltage source inverter. So output voltage is always constant, but the output current is going to depend upon the load. As the output current has not a pure sine wave, it is going to have lot of harmonics. So therefore, input side is also going to have lot of harmonics. So that is the meaning of this one. So triangular PWM control when applied to three-phase BJT based voltage source inverter introduces a very higher order harmonics in the voltage on the AC side. PWM switching is preferred in voltage source inverters for the purpose of PWM switching is preferred in voltage source inverters for the purpose of controlling output voltage. Yes, with the help of PWM switching, we can control the width of the output voltage. So therefore, the output voltage we can control, and the output harmonics also. So we can eliminate whatever the harmonics that we don't want by using the proper pulse width. So we can even reduce the output harmonics. Reducing filter size. Yes, if some of the harmonics we have already removed, then definitely we can reduce the filter size also. So these are the advantages with the help of this PWM switching. So controlling output voltage, output harmonics are also controlled, and then reducing the filter size. So multiple pulse width modulation is used to reduce the harmonic content in the inverter. So multiple pulse width modulation is used to reduce the harmonic content in the inverter. Yes, by using the multiple pulse width modulation, we can even decrease, even we can remove the whatever the harmonic that we really want to remove them. The higher order harmonics can be easily filtered using passive filters. Yes, the higher order harmonics can be easily filtered by using passive filters because as the harmonic frequency increases, the peak value decreases. So therefore, simply we can easily remove with the help of passive filters. The higher order harmonics can be easily filtered using passive filters because as the harmonic frequency increases, the peak value decreases. So simply we can remove with any passive filters, means without any active components like RC. By using only passive components, if you make any filter with only passive components, that is called as a passive filter. In a single phase full bridge inverter, the advantage of unipolar switching over the bipolar switching is apparent doubling of the switching frequency or carrier frequency. In a single phase full bridge inverter, the advantage of unipolar switching over the bipolar switching is apparent doubling of the switching frequency or carrier frequency. So I have already told you very important point here. In a unipolar switching and the bipolar switching, the carrier frequency of unipolar switching is very higher when compared to bipolar switching. I have already told this important point because in a unipolar there are a lot of switching, there are a lot of pulses in half cycle. So because of that, the carrier frequency, more the number of pulses, more the carrier frequency. So therefore we can say that the carrier frequency in unipolar switching is very higher than the carrier frequency in the bipolar switching. So in a single phase full bridge inverter, the advantage of unipolar switching over the bipolar switching is apparent doubling of the switching frequency or the carrier frequency. So carrier frequency in the unipolar switching is very higher when compared to carrier frequency of the bipolar switching because in a half cycle there are more number of pulses we are going to get in the output voltage by using the unipolar switching when compared to bipolar switching. So because of that reason only we can say that the carrier frequency or the switching frequency is very higher in the unipolar switching when compared to bipolar switching. In a bipolar, there is a more fluctuations in line voltage between positive VDC and negative VDC in half cycle. So losses increases and switching frequency is less. So IGBT devices are used. In a bipolar, there is more fluctuations in the line voltage between plus VDC and minus VDC in half cycle. So losses increases and switching frequency is less. So IGBT devices are used. So in a bipolar, what is going to happen is basically in a bipolar in half cycle, there is plus VDC and also minus VDC. So the switching is very higher. So as the switching is higher, the losses are also very higher. So the losses increases. So switching frequency is less. So IGBT devices are used because in a bipolar, we are going to get plus VDC and also minus VDC. So we are going to get plus VDC and also minus VDC. So I have already told you the switching frequency is more in unipolar when compared to bipolar. So there the switching frequency is more in the unipolar when compared to bipolar. So the switching frequency is more means we are going to use the MOSFET. The switching frequency is less means we are going to use the IGBT. So MOSFET devices are used for the unipolar switching whereas the IGBT devices are used for the bipolar switching. So I have already told you the carrier frequency of unipolar is very higher than the carrier frequency of the bipolar. So MOSFET devices are used for the unipolar switching and the IGBT devices are used for the bipolar switching. So in a bipolar, there is more fluctuation in line voltage between plus VDC and minus VDC in half cycle. So losses increases and switching frequency is less. So IGBT devices are used. In a unipolar, there is no fluctuations in half cycle. So losses decreases and switching frequency is more. So MOSFET devices are used. I have already told you in a unipolar, in a half cycle, the output is always positive. So the carrier frequency is very higher here when compared to bipolar. So MOSFET devices are used in the unipolar and IGBT devices are used in the bipolar. In sinusoidal PWM, width of each pulse is varied in proportion to amplitude of a sine wave evaluated at the center of the same pulse because the RMS value of the output voltage can be varied by varying the modulation index. In a sinusoidal PWM, the width of each pulse is varied in proportion to the amplitude of the sine wave evaluated at the center of the same pulse. Because the RMS value of the output voltage can be varied by varying the modulation index. So basically what we are trying to say is here in sinusoidal PWM, we are going to compare the reference signal and the carrying signal. So based on that we are going to get the pulse. So this pulse width is somewhat depending upon the amplitude of the sine wave. So therefore we can say if the amplitude is very higher, the width is very higher. If the amplitude is very lesser, then we can say the width is very lesser. So in sinusoidal PWM, the width of each pulse is varied in proportion to the amplitude of the sine wave evaluated at the center of the same pulse. Because the RMS value of the output voltage can be varied by varying the modulation index. So because of that, as we are going to vary the amplitude of the sinusoidal waveform, the width of the pulse can be easily varied. So therefore, the RMS value of the output voltage can also be easily made with the help of the modulation index. Modulation index is equal to M is equal to Vm by Vc, where Vm is the peak value of the reference signal and Vc is the peak value of the carrier signal. As wear of the peak increases, then M increases and RMS value of the output voltage increases. See, as wear of the peak increases, then M increases and RMS value of the output voltage increases. And what we told you, very simple point. It's because M is modulation index, it is a ratio of the VR by Vc. So as the peak value of the reference signal increases, then M increases. As M increases, you can say simply the width of the pulses increases. So therefore, the RMS value of the output voltage will increase. Meaning of this one. MOSFET have internally anti-parallel diode, so it cannot withstand reverse voltage. So power MOSFETs have internally anti-parallel diode, so it cannot withstand reverse voltage. So this can be used only in voltage source inverter, but not current source inverter. So here MOSFETs have internally anti-parallel diode, so it cannot withstand reverse voltage. So this can be used only in voltage source inverter, but not current source inverter. So if you want to use it in current source inverter, there are no anti-parallel diodes. So if there are no anti-parallel diodes means they have to even withstand the negative voltage. So MOSFETs cannot withstand the negative voltage. So therefore MOSFETs are not used in the current source inverter. They are used only in the voltage source inverter, because in voltage source inverter we can use the feedback diodes. There are feedback diodes are already present. So therefore simply we can say that in the voltage source inverter, the devices no need to withstand the reverse voltage. But in current source inverter, as there are no feedback diodes, definitely these diodes should even withstand the reverse voltage. Then only they are going to get torn off. So therefore that is the reason always MOSFETs are never used in the current source inverter, but they are used only in the voltage source inverter. So MOSFETs have internally anti-parallel diode, so it cannot withstand the reverse voltage. So this can be used only in the voltage source inverter, but not current source inverter, because I have already told you in the current source inverter that natural combustion is possible. So natural combustion is possible in the current source inverter circuits, I have already told you. So because of that, they should even withstand the reverse voltage. As MOSFET is having internally anti-parallel diode, so it cannot withstand the reverse voltage. So we cannot use the MOSFET in the CS side. We can only use in the VS side, because there are feedback diodes are present. So no need for MOSFETs, no need for devices in VS side to withstand the reverse voltage. So MOSFET is used in VS side, but not in CS side. As it's used in current source inverter, must have reverse voltage blocking capability. So whatever the devices that we are going to use in the current source inverter should even withstand the reverse voltage capability. Therefore, devices such as GTO, power transistors and power MOSFETs cannot be used in a CS side. So a diode is added in series with the devices for reverse blocking. So if you want to use them, you have to connect a diode in series with them, and only you can use it for CS side. So therefore GTO and the power transistors and power MOSFETs. So power GTO, just like power GTO, power transistors and the power MOSFETs, they have internally anti-parallel diode. So because of that, they cannot withstand the reverse voltage. So they are going to not withstand the reverse voltage. So if you want to use them CS side, then you have to connect a diode in series with them. Then only you can use it for CS side. So devices in current source inverter must have to withstand even the reverse voltage. So therefore, devices such as GTO, power transistors and power MOSFETs cannot be used in a CS side, because they have anti-parallel diode. So a diode is added in series with the devices for reverse blocking. So if you want to use them, you have to connect a diode in series with them. Then only we can use it for CS side. In case of voltage source inverter, freewheeling can be needed for the load of the inductive nature only. So for inductive loads, load current will not be phased with the voltage across load, and freewheeling diodes connected in anti-parallel with transistors allow the current to flow when the main transistors are torn off. So we can say that in voltage source inverter, there are feedback diodes. So whenever the main transistors are torn off, these feedback diodes are going to get torn off. So therefore, these devices no need to withstand the reverse voltage. So that is the reason we can use the MOSFET devices in the voltage source inverter, but not in CS side. So whatever the devices that you are going to use in voltage source inverter, they don't need to even withstand the reverse voltage. But whatever the devices that you are going to use in CSI, they must even withstand the reverse voltage. So in case of voltage source inverter, freewheeling can be needed for the load of the inductive nature only. For inductive loads, load current will not be in phase with the voltage across load, and freewheeling diodes connected in antiparallel with the resistance allow the current to flow when the main resistors are torn off. If the main resistors are torn off, these diodes are going to connect. These freewheeling diodes are going to connect only for, except our load, they are going to connect for other loads. So because of that, when the freewheeling diodes are going to get turned on, these resistors are going to get turned off automatically. Operation of an inverter-fed induction motor can be shifted from motoring to regenerative braking by decreasing the inverter frequency. So the operation of an inverter-fed induction motor can be shifted from motoring to regenerative braking by decreasing the inverter frequency. So basically, operation of an inverter-fed induction motor can be shifted from motoring to regenerative braking by decreasing the inverter frequency. It indicates that inverter is going to convert the fixed DC to variable AC of different frequency. So variable means variable frequency. So as we are going to give to induction motor, then we are going to shift from motoring to regenerative braking. Motoring means V0 is positive, I0 is positive. Whereas regenerative braking means V0 is positive but I0 is negative. That is the meaning of this regenerative braking. So by reducing the inverter frequency. So for inverter frequency which is greater than 50 Hz, it is going to act like a motoring, whereas less than 50 Hz, it is going to act like a regenerative braking. So if the Fs, the supply frequency to the induction motor is greater than 50 Hz, it is going to act like a motoring. If it is lesser than 50 Hz, it is acting like a regenerative braking. So the pulse width modulated inverter for the control of an AC motor is fed from the uncontrolled rectifier. The pulse width modulated inverter from the control of an AC motor is fed from the uncontrolled rectifier. The pulse width modulated inverter for the control of an AC motor is fed from the uncontrolled rectifier. So suppose if you want to control the speed of an AC motor, the pulse width modulated inverter we are going to get from the uncontrolled rectifier. So uncontrolled rectifier we are going to use here. Then with the help of this uncontrolled rectifier we are going to convert the AC into DC. So with the help of uncontrolled rectifier we are going to get the AC to DC. Then this DC we are going to give to the pulse width modulated inverter. Then we are going to generate the AC, and the AC is used for the AC motor. So the pulse width modulated inverter for the control of an AC motor is fed from the uncontrolled rectifier. Means with the help of uncontrolled rectifier we are going to convert the DC into AC, AC into DC. Then this DC is used by the inverter by using the pulse width inverter we are going to convert into AC or use the control of the speed of the AC motor. The output voltage is obtained by adjusting the on-off period of the inverter components, and this method is called as a PWM control. The output voltage is obtained by adjusting the on-off period of the inverter components, and this method is called as the PWM switching. So basically in PWM switching we are going to switch the thyristors. So we are going to switch the thyristors. For certain time period we are going to on them, for certain periods we are going to off them. So with the help of this only, we are going to get the output voltage for a small amount of pulses. I have already told you in a single phase full bridge inverter, whenever the T1, T2 are on, V0 is equal to plus Vs. Whenever the T3, T4 are on, V0 is equal to minus Vs. So like this, we are going to control the on and off of the switches. So therefore, we can get the variation of the pulse of the output voltage. This is called as a pulse width modulation. CSI, current source inverter, do not require any feedback diodes. In the current source inverter, we are not going to use any feedback diodes. Whereas the voltage source inverter requires the feedback diodes. Yes, in the voltage source inverter, we are going to use the feedback diodes. And device in current source inverter have to withstand the reverse voltage. I have already told you, whatever the devices that you are going to use in the current source inverter, they should be ready to even withstand the negative voltage across them. So GTO and the power transistors and the MOSFETs cannot be used in CSI because they have anti-parallel diodes. So they can't withstand the reverse voltage. So these devices cannot be used in the CSI. If you want to use them, then you have to connect a diode in series with them, and then we can use them in the CSI. A current source inverter is obtained by inserting a large inductance in series with DC supply. So if you connect a large amount of inductance in series with the DC supply, then you are going to get this a current source inverter. A PWM switching scheme is used with a three-phase inverter to reduce the total harmonic distortion with moderate filtering. A PWM switching scheme is used with a three-phase inverter to reduce the total harmonic distortion with moderate filtering. I have already told you, with the help of PWM switching, what is going to happen is, with the help of PWM switching, we can reduce whatever the harmonics we want. So if you are going to remove the harmonics, so here this goes on decreases. As we are going to reduce the harmonics, so we can make a filter size of very small size so that remaining harmonics also we can easily reduce. It is the helpful of the PWM switching scheme. Using PWM technique, we get variable voltage and variable frequency within inverter itself by eliminating some of the lower order harmonics which are mainly responsible for. So by using PWM technique, we get variable output. Using PWM technique, we get variable voltage and variable frequency within inverter itself by eliminating some of the lower order harmonics which are mainly responsible for. They are mainly responsible for distorting waveform. To eliminate higher order harmonics, we use filter. So basically, it is saying that here, by using PWM technique, we get variable voltage and variable frequency within inverter itself by eliminating some of the lower order harmonics which are mainly responsible for distorting waveform. To eliminate higher order harmonics, we use filter. It means that I have already told you with the help of PWM, we can eliminate whatever the frequency, harmonic frequency we want. But we try to eliminate the lower order harmonics because they have huge amount of peak value. Whereas the higher order harmonics will have less amount of peak value. So if you remove the lower order harmonics with the help of by choosing proper pulse width, then you can easily remove the higher order harmonics with the help of filter because they have very less amount of peak value. That is the meaning of this one. So with the help of PWM switching, we can remove whatever the harmonics we really want. But we prefer to remove those harmonics which are lower order because they are going to distort the waveform in a huger manner because they have huge amount of peak value. So we try to remove the lower order harmonics by choosing the proper pulse width. So as the higher order harmonics have a less amount of peak value, we can easily remove with the help of any filter. So with the help of this, VHD decreases and as moderate filtering is also going to happen. The amplitude of output current from CSI is independent of the load because the amount of the output voltage depends upon the nature of the load impedance. The amplitude of the output current from the current source inverter is independent of the load because the magnitude of the output voltage depends upon the nature of the load impedance. So I have already told you, for a current source inverter, the output current is independent of the load elements, whereas the output voltage is depending upon the nature of the load impedance. Multiple pulse width modulation is used to reduce the harmonic content in inverters. Multiple pulse width modulation is used to reduce the harmonic content in inverters. So with the help of multiple pulse width modulation, we can remove the harmonics which we really don't want. So with the help of that, PSB also goes on decreases. So that is the meaning of this one. So multiple pulse width modulation is used to reduce the harmonic content in the inverters. And the higher order harmonics can be easily filtered by using passive filters because I have already told you higher order harmonics will have low amount of peak value. We can remove easily with any passive filters. Passive filters means the filters which are made of only passive elements like resistor, inductor, capacitor without using any active components like op-amp. In PWM, for more number of pulses per half cycle, the amplitude of lower order harmonics reduces, but those of some higher harmonics are increased significantly and they can be easily filtered. In PWM, for more number of pulses per half cycle, the amplitudes of the lower order harmonics reduces, but those of some higher harmonics are increased significantly and they can be easily filtered. So if you are going to increase more number of pulses in an half cycle, what is going to happen? If you are going to increase the more number of pulses in a half cycle, the amplitude of the lower order harmonics are going to get reduced, but the amplitude of the higher order harmonics are going to get increased. That is the meaning of this one. So in PWM, for more number of pulses per half cycle, The amplitude of the lower order harmonics reduces, but those of some higher order harmonics are increased significantly and they can easily filter. So I have already told you in PWM, for more number of pulses in half cycle, the amplitude of the lower order harmonics are going to reduce, whereas the amplitude of the higher order harmonics are going to increase. So we can easily filter them. In a three-phase inverter employing sinusoidal PWM, when the peak-to-peak value of both the carrier and the modulating waves are made equal, then this works in the linear modulation region. In a three-phase inverter employing sinusoidal PWM, when the peak-to-peak value of both the carrier and the modulating waves are made equal, then this works in linear modulation region. See, basically in a three-phase inverter, suppose we are going to use the sinusoidal PWM. If the peak value of the carrier signal is equal to the peak value of the reference signal, then this is going to operate in the linear modulation region. In a three-phase inverter employing sinusoidal PWM, when the peak-to-peak values of both the carrier and the modulating waves are made equal, then this works in the linear modulation region. So whenever in a three-phase inverter, if you are going to use the sinusoidal PWM, if the peak value of carrier signal is equal to the peak value of the difference signal, then it is going to work in the linear modulation region. Modified MC Murray full bridge inverter works on current computation. Modified MC Murray full bridge inverter works on current computation. So this is a bridge. Modified MC Murray full bridge inverter works on the current computation. So this bridge, which is modified MC Murray full bridge inverter, works on the current computation. It's a very important statement, which is most asked in the examination. So modified MC Murray full bridge inverter works on the current computation. So modified MC Murray full bridge inverter works on the current computation. Current source inverters are suitable for supply power to only capacitive loads. Current source inverters are suitable for supplying power to only capacitive loads. That is the reason I have already told you a circuit which is parallel RC load. So with the help of this, we are going to supply power to the only capacitive loads. So current source inverters are suitable for supplying power to only capacitive loads. So this current source inverters can supply the power only to only the capacitive loads, because we can say that the current source inverters are suitable for supplying power to only capacitive loads. The main application of multi-level inverter is in reactive. Application of multi-level inverter is in reactive power compensation. The main application of multi-level inverter is in reactive power compensation. So the main application of multi-level inverter is in the real power, in the reactive power compensation. The main application of the multi-level inverter is in the reactive power compensation. So the reactive power compensation is the main application of the multi-level inverter. And the reactive power compensation is the main application of the multi-level inverter. The device which is used for switching in a switched mode power supply is MOSFET, because MOSFET is used in high frequency operations. In SMPS, we require high frequency operating device like MOSFET, because I have already told you switch mode power supply. In this, we are going to use the MOSFET as the switching element, because there we need the high frequency of applications. So high frequency of switching is used only in the MOSFET. So because of that, MOSFET which is preferred in this SMPS. So the device used for switching in a switched mode power supply is MOSFET. Because MOSFET is used in high frequency operations, in SMPS we require the high frequency operations. So in SMPS we require high frequency devices like MOSFET. A switched mode DC power supply has high efficiency and lightweight. So because it is used as DC to DC switching converter switched at high frequency. So a switched mode DC power supply has high efficiency and lightweight, because it uses a DC to DC switching converter switched at high frequency. So I have already told you here basically this SMPS is nothing but here it is going to use a chopper, DC to DC chopper. Here we are going to use the high frequency application. So MOSFET is used here and it has very high amount of efficiency and lightweight. So a switched mode DC power supply has high efficiency and lightweight because it uses a DC to DC switching converter switched at very high frequency by using the MOSFET switch. SMPS is based on the chopper principle, means it is going to use the chopper circuit with very high switching speed. So it is going to have huge amount of switching speed. Hence, the advantage of SMPS is for the same power rating, SMPS is of smaller size, lighter in weight, and possesses higher efficiency because of its high operating operation. So I have already told you here SMPS is based on the chopper principle. It is going to use the chopper circuit. It has a very high amount of switching speed. And here, as the advantage of SMPS is for the same power rating, SMPS is of very smaller size, lighter in weight, and possesses higher efficiency because of its high frequency operation. So these are some of the advantages of the SMPS: light in weight, higher efficiency, and high frequency operations. And it also uses the chopper principle or DC to DC circuit. The main advantage of SMPS over linear power supply is low power distribution. See, in SMPS, the amount of power dissipation is very low when compared to normal power supply. So, the main advantage of SMPS over linear power supply is low power dissipation. SMPS filter is required and also easy to design. Yes, to make the SMPS is very easy to design. And there are multiple stages in SMPS, and transformer is also used in SMPS with a small physical size. So transformer is also used in this SMPS and also very less size and also very less weight. It is the main reason to widespread use of the SMPS. So in SMPS we are going to use a transformer, and also its size is very less and its efficiency is very less, and it is used at high frequency, and also here we are going to use the chopper principle. So because of all these advantages and also low amount of power dissipation, so because of all these principles it is used very widespread. In SMPS filter is required and also easy to design. It is very easy to design the SMPS. And there are multiple stages in SMPS, and transformer is also used in SMPS with a small physical size and less weight is the main reason to widespread use of the SMPS. The main basic reason of this use is it has very less weight, high efficiency, low losses or low power distribution, and it also includes the use of the transformer and also uses a DC to DC chopper, and all these things because of easy to design. Because of all these reasons only, the widespread of SMPS is used. MOSFET is used as a switch in a low power switched mode power supply or SMPS. MOSFET is used as a switch in a low power switched mode power supply because I have already told you SMPS where we are going to use at high frequency of operations. So MOSFET is the only device it can handle the high frequency of applications or high frequency of switching. In SMPS, high frequency operation is required. For such applications, MOSFET is used because it has less switching, losses. I have already told you in SMPS we need high frequency of applications, high frequency of operations. MOSFET is used for high frequency of operations, and it also has high amount of input impedance, whereas though it has high conduction losses and low switching losses. So MOSFET has high conduction losses and low switching losses. So low switching losses is the main reason for which the MOSFET is used in the SMPS applications. MOSFET has low switching losses and operates at high frequency of which is 20 kW to 100 kW. So MOSFET we are going to use as a switch in this range of application which is 20 kW to 100 kW. It has high conduction losses whereas low switching losses. So because of these reasons only, we are going to use the MOSFET as a switch in SMPS. So MOSFET has low switching losses and high conduction losses and operates at high frequency range of 20 kHz to 100 kHz. The advantages of switching power supplies over linear power supplies are the advantages of the switching power supplies over linear power supplies are the devices are operate as switches only in saturation and cutoff regions. So whatever the devices which are going to use in the SMPS, they are going to operate either in the cutoff region or either in the saturation region, and the power losses are very less. So and the power losses are very less because they are going to operate only in the cutoff region or the saturation region. I already told you means here only in this way we are going to operate. The advantage of switching SMPS over linear power supplies is the devices which are used in the SMPS, they are going to operate either only in the saturation region or the cutoff region. Because of this reason only, the amount of power losses are very less. SMPS possesses higher efficiency because of its high frequency operation and suitable for low power DC applications only. I have already told you SMPS possesses higher efficiency because it has low losses. Because of that only it has higher efficiency because of its high frequency operation and suitable for low power DC applications only. So it is used for only low power DC applications only. So it is used for only low power DC applications only because it has higher efficiency and has higher frequency operation and is suitable for only low power DC applications only. Low power DC applications only we are going to use the SMPS. AC voltage regulators are widely used in the fan drives. AC voltage regulators is also called as the cycloconverters. These are basically very widely used in the fan drives. So in the fan drives we are going to use these AC voltage regulators or the cycloconverters because a cycloconverter converts a fixed AC into a variable AC of different magnitude and different frequency. Output frequency can be lesser than the input frequency. Sometimes the output frequency can be greater than the input frequency. So F0 is equal to N into F5. F0 is called as output frequency and F5 is called as input frequency, where N is always a purely integer. In fan drives or pump drives with induction motors, the torque varies as the square of the speed. Thus, the speed control is required in narrow range and AC voltage controller is suitable for an induction motor with a full load slip of 0.1 to 0.2 in such applications. See, you can see clearly in the fan drives or the pump drives with induction motors. So in the fan drives or the pump drives with induction motors, the torque varies as the square of the speed. Thus, the speed control is required in a very narrow range and AC voltage controller is suitable for an induction motor with a full speed slip of 0.1 to 0.2 in such applications. So we can say that basically whether it is a fan drive or it is a pump drive. So if you are going to use either in a fan drive or pump drive with induction motors, there the torque is directly proportional to the square of the speed. So there we need a very fine control of the speed. There we need a very fine control of the speed. So because of that, AC voltage regulators or the AC voltage controllers or the cycle converters are used for this induction motor with a slip range of with a full load slip range of 0.1 to 0.2 in such applications. So there with a slip from 0.1 to 0.2, a fine amount of speed control can be possible only by the cycloconverter or the AC voltage regulator in the fan drives or the pump drives with induction motors. A cycloconverter is operating on a 50-watt supply. A cycloconverter is operating on a 50-watt supply. The range of output frequency that can be obtained with acceptable quality is 0 to 128 Hz. So I have already told you, so 0 to 128 Hz. So input frequency is 50 Hz means the output frequency can vary from 0 to 128 Hz. Means the output frequency can be less than input frequency. The output frequency can even be greater than input frequency. So a cycloconverter is operating on a 50 Hz supply. The range of output frequency that can be obtained with acceptable quality means the acceptable quality of output can be obtained with the output frequency range of 0 to 128 Hz. So therefore we can say that if a cycloconverter input we are going to apply with a frequency of 50 Hz, then the range of output frequency that can be obtained with acceptable quality is from 0 to 128 Hz. Cycloconverter converts input power at one frequency to output power at a different frequency with one stage conversion. So I have already told you, the cycloconverter basic function is to convert a fixed AC to a variable AC of variable magnitude and variable frequency. So output frequency is equal to n times input frequency. So F0 is called as output frequency, F5 is called as input frequency, N is always a purely integer. So sometimes the output frequency can be lesser than input frequency, sometimes the output frequency can be greater than the input frequency. So a cycloconverter converts the input power at one frequency to output power at a different frequency with one stage conversion. Within a one stage conversion only we are going to convert like this. An intergroup reactor is used in a single phase cycloconverter circuit to limit the circulating current. An intergroup reactor is used in a single phase cycloconverter circuit to limit the circulating current. So if you want to limit the circulating current, then you have to use the reactor in a single phase cycloconverter. So in a single phase cycloconverter, if you want to limit the circulating current, then you have to use the reactor. In a switched capacitor network, for war compensation, the SCRs are commutated by resonant commutation. So in a switched capacitor network for war compensation, the SCRs are commutated by resonant commutation. So in a switched capacitor network for war compensation, the SCRs are commutated by resonant commutation. So in a switched capacitor network, so for war compensation, the SCRs are commutated by resonant commutation. So if you want to Turn off the SCRs. If you want to turn off the SCRs in a switched capacitor network for VAR compensation, it is done by resonant commutation. So in a switched capacitor network for VAR compensation, the SCRs which are used in the circuit can be counted by the resonant commutation. A cycloconverter fed induction motor drive is more suitable where precise control required like machine tool drive. A cycloconverter fed induction motor drive is more suitable where precise control required like machine tool drive. I've already told you, whenever a cycloconverter fed induction motor drive is more suitable where precise control required like machine tool drive. In a forward converter, a tertiary winding is used to demagnetize the core before the application of the next switching pulse. In a forward converter, a tertiary winding is used to demagnetize the core before the application of the next switching pulse. In a forward converter, a tertiary winding is used to demagnetize the core before the application of the next switching pulse. So in this forward converter, we are going to use the tertiary winding. So with the help of this tertiary winding, we are going to demagnetize the core before the application of the next switching pulse. So in this forward converter, we are going to use the tertiary winding. With the help of this tertiary winding, we are going to demagnetize the core before the application of the next switching pulse. So in a forward converter, tertiary winding is used to demagnetize the core before the application of the next switching pulse. Forward converter, tertiary winding is added to the transformer. In a forward converter, tertiary winding is added to the transformer so that the magnetizing current can return to the input source Vs when the transistor turns off. The transformer magnetizing current must be reset to 0 at the end of each cycle. Otherwise, the transformer can be driven into saturation, which can cause damage to the switching device. So that is the reason in the forward converter, we are going to use the tertiary winding to demagnetize the core before the application of the next switching pulse. So in forward converter, a tertiary winding is added. In the forward converter, a tertiary winding is added to the transformer so that the magnetizing current can return to the input source when the transistor turns off. The transformer magnetizing current must be reset to 0 at the end of each cycle. Otherwise, the transformer can be driven into saturation, which can cause damage to the switching device. So always, because of this, transformer can be driven into saturation, so which can cause damage to the switching device. That is the reason we need to demagnetize the core before the application of the next switching pulse. So therefore, we can safeguard the switching device. So always we have to demagnetize the core before the application of switching pulse. Otherwise, the switching device can get damaged because the core can go into saturation mode. So in forward converter, tertiary winding is added to the transformer so that the magnetizing current can return to the input source Vs when the transistor turns off. The transformer magnetizing current must be reset to 0 at the end of each cycle. So at the end of each cycle, we need to make the magnetizing current to 0 of the step transformer. So at the end of each cycle, we need to make the magnetizing current to be 0 for the transformer. Otherwise, the transformer can be driven to saturation, which can cause damage to the switching device. So at end of each pulse, at the end of each cycle, we need to make the magnetizing current of the transformer to be 0. Otherwise, the transformer can get into saturation and it can damage the switching device. In a single phase to single phase cycloconverter, the amount of harmonics is quite large. It can be reduced by using a 3-phase input supply. So here in a single phase to single phase cycloconverter, the amount of harmonics is quite large. It can be reduced by using a 3-phase input supply. So if you want to do the single phase to single phase conversion of cycloconverter, the amount of the harmonics is very large. It can be reduced by a 3-phase input supply. So if the input supply is 3-phase, then we can reduce the harmonics very quite. Otherwise, the harmonics are very large. So in a single phase to single phase cycloconverter, the amount of the harmonics is very large. So if you want to reduce them, just use the 3-phase input supply. So in a single phase to single phase cycloconverter, the amount of the harmonics is very quite large. It can be reduced by using a 3-phase input supply. Control rectifier are used to keep variable DC from fixed AC by varying firing angle. So control rectifier are used to get variable DC from fixed AC by varying firing angle. So control rectifier means simply it is going to convert the fixed AC into variable DC. So by varying the alpha, we are going to get the variable DC voltage output. So control rectifier are used to get variable DC from fixed AC by varying the firing angle. By varying duty cycle, choppers are used to get variable DC from fixed DC voltage. By varying duty cycle, choppers are used to get variable DC from fixed DC voltage. So choppers basically used to convert fixed DC to variable DC. Variable output DC we can get by varying the duty ratio or duty cycle. So by varying duty cycle, chopper are used to get variable DC from fixed DC voltage. By varying firing angle, inverters are used to get variable voltage and variable frequency AC from fixed DC. So by varying the firing angle, inverters are used to get variable voltage and variable frequency AC from fixed DC. I already told you inverter's basic function is to convert fixed DC to variable AC. Variable AC means variable magnitude of the AC and also variable frequency. That is the meaning of this variable AC. So by varying firing angle, inverters are used to get variable voltage and variable frequency AC from fixed DC. So inverter's basic function is to convert fixed DC to variable AC means variable magnitude of the voltage AC and the variable frequency of the AC. Cycloconverters are used to convert fixed AC to variable frequency AC. I have already told you cycloconverters is also called as the AC voltage regulators are used to convert the fixed AC to variable frequency AC means variable magnitude and also variable frequency. Motor armature supplied through phase control SCRs receives a smoother voltage shape at high motor speed. A motor armature supplied through phase control SCRs receives a smoother voltage shape at high motor speed. So we can say clearly that here the motor is going to receive a DC means a motor is going to receive a DC supply from the phase control SCRs. This shape will be very smoother at very high speed operations. So at very high speed operations, whatever the DC voltage obtained through phase control SCRs are very smoother in shape for this motor. So a motor armature supplied through phase control SCRs receives a smoother voltage waveform at high motor speed. The speed of the three-phase squirrel cage motor can be controlled by varying the frequency of the supply. It is possible by using cycloconverter. The speed of the three-phase squirrel cage motor can be controlled by varying the frequency of the supply. It is possible by cycloconverter. So I have already told you, cycloconverter converts a fixed AC to variable AC. So variable AC means variable voltage AC and variable frequency. So if you vary the frequency input to a squirrel cage induction motor, you can control the speed of the induction motor because Ns is equal to 120 by P. As F changes, Ns changes. As Ns changes, Nr changes. So we can say that the speed of the three-phase squirrel cage motor can be controlled by varying the frequency of the supply. It is possible by using cycloconverter. In a self-controlled synchronous motor fed from a variable frequency inverter, the rotor rotates at synchronous speed, which is Ns is equal to 120 by P. So the rotor speed is decided by the frequency of the stator. So we can say clearly here, in a self-controlled synchronous motor fed from a variable frequency inverter, the rotor rotates at synchronous speed, which is Ns is equal to 120 by P. So the rotor speed is decided by the frequency of the stator. Because in a synchronous motor, the rotor speed is equal to synchronous speed, which is 120 by P. As F changes, Ns changes, so Nr is also changes. So F is called as the stator frequency. It is decided by the output of the inverter. So therefore, simply we can say that in a self-controlled synchronous motor fed from a variable frequency inverter, the rotor rotates at synchronous speed, which is Ns is equal to 120 by P. So the rotor speed is decided by the frequency of the stator. A large DC motor is required to control the speed of the blower from a three-phase AC source. The suitable AC to DC converter is three-phase off-control bridge converter because used for only motoring purpose, and it will have improved power factor operation. A large DC motor is required to control the speed of the blower from a three-phase AC source. A large DC motor is required to control the speed of the blower from a three-phase AC source. So therefore, for this DC motor, we are going to use three-phase AC source as the input, and we need to control the speed of the blower. A suitable AC to DC converter is three-phase half control bridge converter. So with the help of this three-phase half control bridge converter, we are going to convert the three-phase AC into a this DC voltage. This DC voltage we are going to give to the motor through this DC motor, and then it is going to control the speed of this blower. Because used for only motoring purpose, and it will have input power factor operation. Because of this three-phase half control bridge converter, three-phase half control bridge converter. So three-phase half control means we are going to get only 3 pulses in the output voltage. So it will be always positive. So V0 is always positive and I0 is also positive. So only used for motoring purpose. So only used for the motoring purpose. So because of that only we can say it is used for only motoring purpose. And also it will have input power factor operation. So with the help of this three-phase half control bridge converter, we can have used for only motoring purpose and also input power factor operation. So therefore, if you want to convert the three-phase supply to DC supply, we have to use the three-phase half control bridge converter and give this DC supply output of give the DC supply output of three-phase half control bridge converter to this DC motor. So then it can control the speed of the blower. By using the three-phase half control bridge converter, it is used for only for the motoring purpose, and it will have huge amount of input power factor operation. So a large DC motor is required to control the speed of the blower from a three-phase AC source. A suitable AC to DC converter is three-phase half control bridge converter because used for only motoring purpose, and it will have improved power factor operation. In a MC Murray inverter, diodes are connected in. In a MC Murray inverter, diodes are connected in. In a MC Murray inverter, diodes are connected in inverse parallel to thyristors because to make the turn off of the thyristor successful and to provide power to the reactive component of the load current. In a MC Murray inverter, diodes are connected in inverse parallel to thyristors because to make the turn off of the thyristor successful and to provide path to the reactive component of the load current. So here we are going to connect the diodes in anti-parallel to the thyristors. Because of this, the turn off of the thyristors can be very successful, and also we can say that the reactive component of the load current can also pass through the diodes. Or simply we can say the current can even flow through the diodes. In a MC Murray inverter, diodes are connected in inverse parallel to thyristors because to make the turn off of the thyristor successful and to provide path to the reactive component of the load current. Cycloconverter changes the frequency which is not possible with any coordinate chopper. A cycloconverter changes the frequency which is not possible with any coordinate chopper. I have already told you regarding the different types of class of choppers like class A, class B, class C, class D and class C. Class A means first column, class B means second column, class C means first and second column, class D means first and fourth column, class E means all the columns. So cycloconverter can only this converter which can change the frequency of the output, whereas no chopper can convert the output frequency. So therefore simply we can say that a cycloconverter changes the frequency which is not possible with any coordinate chopper. Triacs cannot be used in AC voltage regulator for highly inductive loads. Means for highly inductive loads, you can't use the triacs. We can't use the triacs in the AC voltage regulator because here with a narrow load conduction angle, because it can result in unacceptable symmetrical operation. So you can say that triacs cannot be used in AC voltage regulator for high inductive loads with a narrow conduction angle because it can result in unacceptable symmetrical operation. So because of that, unacceptable symmetrical operation can take place. That is the reason triacs are not used in the AC voltage regulator for highly inductive loads with a narrow conduction angle because that it can result in unacceptable symmetrical operation. So symmetrical operation may not be possible because of this. So unacceptable symmetrical operation may result. That is the reason triacs are not used in this AC voltage regulator for highly inductive loads. MOSFETs always have internal body diode, so no need to show them in the symbolic diagram. So MOSFETs always have internal body diode, so no need to show them in the symbolic diagram. So MOSFETs are going to internally, the power MOSFETs are definitely going to have the internal body diode. So no need to show them in the symbolic diagram because MOSFETs in the body itself they are going to have the internal body diode, which is like anti-parallel. So therefore that is the reason it never withstands the reverse voltage. So therefore we can say we don't have to represent it in the symbolic diagram. And SCR has half cycle current, and SCR has half cycle current rating of 3000 ampere for 50 hertz supply. One cycle surge current rating will be. So an SCR has half cycle current rating of 3000 ampere for 50 hertz cycle. Then one cycle surge current rating will be. See, equating the energies involved in one cycle surge and half cycle surges. So we are going to equate the energy in one cycle and also half cycle. So the energy formula is called I square T. So here I square Vt, but actually I square RT. So R is the constant, we can remove it. So I square into T1 is equal to I square into T2. So this is 3000 whole square into T1, which is T by 2 is equal to I square into T, because it is half cycle and this is a total cycle. So Tt cancels. If we solve this one, we are going to get 21 ampere. So here we have to equate the energies in this. We need to figure this. We need to equate the energies in the cycle for the one cycle and the half cycle. So I1 square R T1 is equal to I2 square R T2, as R are equal. So they are going to get cancelled. So now we can do the simplification. The sharing of the voltages between thyristors operating in series is influenced by the static VI characteristics and the leakage currents. The sharing of voltage between the thyristors operating in series is influenced by the static VI characteristics and the leakage currents. See, basically, suppose if you want to make a series combination of more than two thyristors, then definitely if you give a supply voltage across them, the amount of voltage drop across each and every thyristor is going to depend purely on the static VI characteristics of each and every thyristor and also leakage currents. The thyristors will have different static VI characteristics, so which in turn results into unequal leakage resistance and currents. The sharing of voltage across thyristors depends on leakage resistance and the currents. I have already told you, suppose you cannot make each and every thyristor has the same static VI characteristics. There may be some difference. So because of that, the leakage resistance and the currents are going to get changed. So therefore, the amount of sharing of voltage drop each and every thyristor is also going to get changed. So the thyristors will have different static VI characteristics, which in turn results into unequal leakage resistance and currents. The sharing of voltage across thyristors depends on the leakage resistance and the currents. RC number is used in parallel with the thyristor to reduce the dV by dt across it, because capacitor opposes change in voltage across thyristor. It results into more time for development of voltage, hence it reduces dV by dt. RC number circuit is used in parallel with thyristor to reduce the dV by dt across it, because capacitor opposes change in voltage across thyristor, results in more time for development of voltage, so it reduces dV by dt. So simply we can say that here, as we are going to use the RC circuit in parallel with thyristor, because it is going to reduce the dV by dt or the electrical stresses. So as capacitor is going to oppose the change in voltage, so for a given amount of change in voltage, it takes a lot of time, so dV by dt ratio is going to get decreased. That is the reason we can say that with the help of this number circuit, it can reduce the rate of change of rise of voltage. So therefore, for a small amount of dV, the dt will be very, very large. So because of that, this ratio will be very smaller with the help of this RC number circuit. So RC number is used in parallel with thyristor to reduce dV by dt across it, because capacitor opposes change in voltage across thyristor, results into more time for development of voltage, hence it reduces dV by dt. As I told you, latching current is always greater than the holding current, which is nearly 1.5 to 3 times the holding current. So latching current is nearly 1.5 to 3 times the holding current. So in the GTO, gate turn of thyristor, the current gain is nothing but anode current by gate current. See, current gain is called as the anode current by the gate current. But the gate current is very, very high in GTO, so therefore the turn of gain is very small. So simply we can say that the turn of gain is equal to anode current by gate current. As the gate current is very high in the GTO, so therefore this ratio is very small. So simply we can say that the turn of gain, or we can say the turn on gain, you see, the turn on current gain in GTO is very small, because the gate current is very huge value. In GTO, higher values of gate current is required to make the turn off. Hence, turn off gain would be poor among all devices. So I have already told you, here turn off gain is equal to anode current by gate current. So turn off gate current is equal to, so turn off gain is equal to anode current by gate current. So gate current is very huge in order to turn off the GTO. So therefore the ratio is very less. So therefore simply we can say that in GTO higher values of gate current is required to make turn off. Hence turn off gain would be poor among all devices. So turn off gain is equal to anode current by gate current. So the gate current required to turn off the anode to turn off the GTO is very higher. So this ratio is very small. In a power circuit of 3 kV, 4 thyristors each of rating 800 volt are connected in series. What is the percentage series derating factor? In a power circuit of 3 kV, 4 thyristors each of rating 800 volt are connected in series. What is the percentage series derating factor? So derating factor is equal to, derating factor is equal to 1 minus string efficiency. So derating factor is equal to, the percentage of derating factor is equal to 1 minus string efficiency into 100. So therefore percentage of derating factor is equal to 1 minus string efficiency into 100. So 1 minus string efficiency is string voltage by number of series connected. String voltage by number of series connected thyristors into voltage rating of each thyristor. So therefore 1 minus the overall string voltage is with the 3 kV means 3000 by number of thyristors we are going to use it, which is 4 into SCR. Rating of SCR is 800 volt. So if we solve this one, we are going to get the percentage of derating factor is equal to 6.25. So string efficiency means, so the 100 means we can say the percentage of derating factor is equal to 1 minus string efficiency into 100. A triac can be used only in cycloconverter. A triac can be used only in cycloconverter. I have already told you, triac can be used only in cycloconverter, but it is not used for highly inductive loads in cycloconverter. So this is the point that you always have to remember. Triacs is basically used in the cycloconverters, but it is not used for highly inductive loads because of unacceptable symmetrical operations. In a commutation circuit employed to turn off an SCR, satisfactory turn off is obtained when the circuit turn off time is greater than the device turn off time. So in a commutation circuit employed to turn off an SCR, satisfactory turn off is obtained when the circuit turn off time is greater than the device turn off time. So circuit turn off time is the time for which we are going to keep the reverse voltage across the device. That time should be always greater than the device turn off time. Then only we can confirm that the device is 100% off. In a dual converter, the circulating current allows smooth reversal of load current with improved speed of response. So in a dual converter, the circulating current allows smooth reversal of load current with improved speed of response. So if you want the load current to reverse its direction, then you have to use the circulating current mode. Means you have to keep the inductor. So therefore, the smooth amount of reversal of load current can be easily happen. Effect of blanking time on output voltage in PWM inverter is high order times harmonics in output voltage. The effect of blanking time on output voltage in PWM inverter is higher order time harmonics in output voltage. The effect of blanking time on output voltage in PWM inverter is higher order time harmonics in output voltage. So the effect of blanking time on output voltage in PWM inverter results in higher order time harmonics in output voltage. Means if in a PWM, if the output voltage for some time, if the output voltage is 0, then because of that a huge amount of harmonics are going to get present in the output voltage. The effect of blanking time on output voltage in PWM inverter is higher order time harmonics in output voltage. Means because of this blanking time, for small amount of time the output voltage is 0 in a PWM inverter. So because of that, a higher order harmonics are going to present in this output voltage. That is the meaning of this statement. So because of this blanking time on the output voltage, means for a small amount of time the output voltage is 0 in a PWM inverter. So because of this, a higher order harmonics are going to present in this output voltage. A single phase fully controlled line commutated AC to DC converter operates as an inverter when 90 degree less than or equal to alpha less than or equal to 180, and there is a suitable DC source in the load circuit. So here a single phase fully controlled line commutated AC to DC converter operates as an inverter when alpha is lying between the 90 to 180 and there is a suitable DC source in the load circuit. See, I have already told you in a single phase fully controlled converter, I have already told you simply for alpha less than 90 is going to act like an inverter. So therefore the real power is going to flow from AC to the load side. Whereas for alpha lying between 90 to 180, the it is going to act like a inverter. So we can say that the amount of real power is going to travel from load to source. And always a DC source must be present in the load side, like a RLE load. Then only it is possible. Modified MC Murray full bridge inverter works on the current computation. So modified MC Murray full bridge inverter works on the current computation. So modified MC Murray full bridge inverter works on the current computation, because here we are going to use thyristor and also diode. They both are going to cut in the antiparallel to each other. And because of this diode, we can turn off the thyristors. This suitable time is available for the thyristors to be turned off, and also the load currents, the huge amount of load currents can pass through this diodes also. So that is the meaning of this modified MC Murray full bridge inverter, which works on the current computation. A three-phase sinusoidal PWM inverter operates from a DC link voltage of 500 volt. For modulation index of 0.8, the RMS value of the fundamental line to line voltages. So basically, a three-phase sinusoidal PWM inverter operates from a DC link voltage of 500 volt. For modulation index of 0.8, the RMS value of the fundamental line-to-line voltages. So we have to find what is RMS value of the fundamental line-to-line voltage. So we can see clearly the phase voltage is equal to the fundamental phase voltage is equal to M into VDC by 2. So this is the phase voltage, which is M into VDC by 2. This is the peak value of the fundamental phase voltage. So this is the peak value of the fundamental phase voltage. So if you want to find what is the RMS of fundamental line-to-line voltage, then its peak value is equal to root 3 into M into VDC by 2 by root 2. So therefore peak value by root 2 is called as the RMS value of the fundamental component of the line voltage. But the phase means the peak value of the fundamental phase voltage, which is M into VDC by 2. But if you want to find what is RMS of fundamental line-to-line voltage, which is peak value by is root 3 into Vm by root 2. So line voltage peak value is root 3 Vm. So root 3 into the phase voltage peak value is M into VDC by 2 by root 2. So if you solve this one, we are going to get 244.8 volt. So therefore, the RMS value of the fundamental line-to-line voltage is equal to peak value by root 2. Peak value is equal to root 3 into maximum value of the phase voltage. In a current source inverter, output current is constant. In a current source inverter, output current is constant and output voltage changes based on load variation. I have already told you, in a constant current source, output current is constant and the output voltage changes based on the load variation. Or simply we can say that in the current source inverter, the output current is a constant, but the load voltage is going to depend upon the load. See, output current is independent of the load. Suppose V is equal to IR, then I is equal to V1 by R1 is equal to V2 by R2 is equal to V3 by R3, because current is always constant. So V1 by R1 is equal to V2 by R2 is equal to V3 by R3. So we can say that in a current source inverter, the output current is a constant, but the only thing is the output voltage is going to depend upon the load, but the output current is independent of the load. A voltage source inverter is used when the source and the load inductance are small and large. See, the voltage source inverter is used when the source inductance is small and the load inductance is large. Similarly, a current source inverter is used when the source inductance is very large and the load inductance is very small. A Schottky diode is a majority carrier device. I have already told you the important parameters of the Schottky diode in the earlier class only. So, a Schottky diode is a majority carrier device. The purpose, so the Schottky diode is basically, it is a majority carrier device. So it is a majority carrier device. The purpose of freewheeling diode in a thyristor controlled AC to DC converter is to reduce the current of its associated thyristor to 0 so that conversion can take place. The purpose of freewheeling diode in a thyristor controlled AC to DC converter is to reduce the current of its associated thyristor to 0 so that conversion can take place. So here we are going to use basically the freewheeling diode. So therefore the current in the thyristor can become 0 and the load voltage cannot be negative. So continuous conduction can also be possible. So that is the main function of this freewheeling diode. So we are trying to make the current in the thyristor to become 0 and the conversion can take place easier and the output voltage will be always positive. SCR conducts for more time, then its average on-state current will also increase. If SCR conducts for more time, then its average on-state current will also increase. Suppose it is conducting for more time means its average on-state current will also increases. So if SCR conducts for more time, then its average on-state current will also increases. So if SCR connects for more time, then its average on-state current will also increases. If it is going to connect for more time means, then its average on-state current will also increases. So now aluminum is cheaper than other conductors. So for best results per unit cost, heat sinks mounted on aluminum. So because we can say that aluminum is cheaper than other conductors. So for best results per unit cost, heat sinks are mounted on aluminum. So we can say that basically what I am trying to say is basically aluminum is very cheaper. It's a very cheaper than other conductors. So because of this reason only we are going to make the heat sinks with the help of aluminum. So with the help of aluminum we are going to make the heat sinks because it is very cheaper when compared to other conductors. So aluminum is cheaper than other conductors. So for best results per unit cost, heat sinks are mounted with aluminum. Yes, they are basically made with aluminum. So for less amount of cost, because the main reason is for less cheaper than the other conductors, we are going to make the heat sinks with the help of aluminum. In a buck boost converter, the maximum value of the switch utilization factor is 0.75. In a buck boost converter, the maximum value of the switch utilization factor is 0.75. So in a buck boost converter, the maximum value of the switch utilization factor is 0.75. A motor armature supplied through phase control SCRs receives a smoother voltage shape at high motor speed. A motor armature supplied through phase control SCRs receives a smoother voltage shape at high motor speed. Because I've already told you here, because of this phase control SCRs, we are going to convert the AC to DC. If the speed of the motor is very higher, then this DC voltage can be have a very smoother voltage waveform shape. A motor armature supplied through phase control SCRs receives a smoother voltage shape at high motor speed. A voltage source inverter is normally employed when both the source and the load have low value of impedance and reactance respectively. A voltage source inverter is normally employed when both the source and load have low voltage of impedance and reactance respectively. See, voltage source inverter is used only when the source inductance is less and the load inductance is high. Similarly, a current source inductor is used when the source inductance is high and the load inductance is low. Line commutated inverters cannot function as isolated AC sources. Line commutated inverters cannot function as isolated AC sources. Line commutated inverters cannot function as isolated AC sources. So line commutated inverters cannot function as isolated AC sources. Force commutated inverters can provide independent AC voltage with adjustable voltage and frequency. So line commutated inverters cannot function as isolated AC sources. Force commutated inverters can provide independent AC voltage with adjustable voltage and frequency. Force commutated inverters can provide independent AC voltage with adjustable voltage and frequency. Force commutated inverters can provide independent AC voltage with adjustable voltage and frequency. Thyristor-based inverters require additional circuitry for commutation. Thyristor-based inverters require additional circuitry for commutation because I have already told you in the inverters and choppers we are going to use the fully controlled devices. So thyristor is semi-control. So if you want to fully control, then if you want to turn off, then we have to go for the forced commutation circuit to turn off this one. IGBT power MOSFET based inverters are more reliable, less costly and less complex. IGBT power MOSFET based inverters are more reliable, less costly and less complex. So if you make the inverters with either IGBT or power MOSFETs, then these are more reliable, less costly and also less complex. I have already told you power MOSFETs cannot be used in the current source inverter, but they can be used only in the voltage source inverter because in the current source inverter, the devices which are going to use in current source inverter, they have to withstand even the negative voltage polarity. But these can't be used because power MOSFETs have inbuilt antiparallel diode. So because of that, it cannot withstand the negative voltage. That is the reason GTO, power MOSFETs and the transistors cannot be used in the current source inverter. If you want to use them in current source inverter, then you have to additionally keep a series diode with them. A single phase full converter feeds power to RLE load with R is equal to 10 ohm, L is equal to 10 millihenry and E is equal to 50 volts. The AC source voltage is 230 volt, 50 hertz for continuous conduction. What is the average value of the load current for firing angle delay of 60 degree? So basically this question is a single phase full converter feeds a power to a RLE load with R is equal to 10 ohm, L is equal to 10 millihenry and E is equal to 50 volts. The AC source voltage is 230 volt, 50 hertz. For continuous conduction, what is the average value of the load current for firing angle delay of 60 degree? So the average value of the output voltage in a single phase 1000 is just 2 Vm by pi cos alpha. So 2 into, they have given the RMS value, but maximum value is equal to root 2 into RMS value by pi into cos 60. We are going to get this value. But average value of the output voltage is equal to average value of the output current into resistor plus average value of the voltage across the inductor is 0 plus E. So if you solve this one, V0 is equal to E plus IR, then I value we are going to get. Voltage harmonics on DC side and current harmonics on AC side of converters are predominant in HVDC transmission. Voltage harmonics on DC side, voltage harmonics on DC side and current harmonics on AC side of converters are predominant in HVDC transmission. So HVDC transmission is less costlier. HVDC transmission is very less costlier if the length of the line is greater than 500 km. So remember this point, if the length of the line is greater than 500 km, the cost of HVDC transmission is less when compared to HVAC. That is the reason for length greater than 500 km, we are going to send the power by HVDC transmission but not by HVAC. So voltage harmonics on DC side and the current harmonics on the AC side of converters are predominant in HVDC transmission. So in HVDC, we are going to convert the AC to DC. So the current harmonics in the AC side and the voltage harmonics in the DC side, they are going to play a very predominant role in the HVDC transmission. MOSFET is main switching element in a switched mode power supply operating in 20 kHz to 100 kHz. I have already told you, whenever if you want to operate in 20 kHz to 100 kHz, there we are going to use the switch mode power supply. In this we are going to use the MOSFET as the switching element. Here the efficiency is very higher, size is very lower. If the RMS source voltage is V volt, if the RMS source voltage is V volt, the minimum and maximum values of firing angle for a single phase half wave control rectifier supplying the load with a back EMF of 400 volts are. If the RMS source voltage is V volt, the minimum and the maximum values of the firing angle for a single phase half wave control rectifier supplying a load with a back EMF of 40 volts. So single phase half wave control rectifier means single phase like this. It is going to have single phase like a we are going to basically use a thyristor with some load. So we can see that here like RE load. So if the RMS value of the voltage is V volt, the minimum and maximum values of firing angles for a single phase half wave means in the output we are going to get only 1 pulse. Half wave control rectifier supplying a load with a back EMF of 40 volts R. So let me assume the load is RE load. So therefore what is the minimum and the maximum firing angles? So alpha minimum is nothing but it is equal to theta. Theta is equal to means E is equal to Vm sin theta. So E is equal to Vm sin theta. Em is equal to root 2 into V. So therefore simply we can say that E is equal to root 2V sin theta. So theta is equal to E by root 2V sin inverse. So sin inverse of E by root 2V. So therefore this is called as a theta is equal to alpha minimum. This is a minimum. Then only the thyristors are going to get forward bias or they are going to become the forward bias. Then only we can go for convection. So therefore this we can say this is the minimum value. If you want the maximum value which is pi minus this value, pi minus of this value which is only in this range you can figure at any point if you want to do the conduction of this one. A DC link chopper compared to AC link is highly efficient and less costly. Means we can say that if you compare the DC link chopper and AC link chopper, then we can say that simply the DC link chopper is very highly efficient and less costly. So a DC link chopper compared to AC link is highly efficient and less costly. Cycloconverter can be considered as AC to AC converter with conversion of one stage. I have already told you within a one stage we are going to convert the fixed AC to variable AC. Variable AC means variable frequency and also variable voltage. So F0 is equal to N into Fi. F0 is called as output frequency and Fi is called as input frequency where N is always a purely integer. For elimination of fifth harmonics from the output of an inverter, what will be the position of pulse in a PWM inverter? For elimination of fifth harmonics from the output of an inverter, what will be the position of pulse in a pulse width inverter? So for eliminating the fifth harmonic, sin ND. Basically, if you want to remove any nth harmonic, sin ND is equal to 0. So for fifth means sin phi d should be equal to 0. So sin phi d is equal to 0. So phi d is equal to, which is here, k pi. So k pi is nothing but k can be 0, k can be 1, k can be 2, k can be 3. So therefore you are going to get like this. But I want 2d. So but 2d is equal to 0 comma 2 by pi comma 6 comma by pi. You are going to get all these things. So 2d is going to lie between 0 to 180 degree only. So therefore also it is nothing but 2d, which is it is going to lie only between 0 to 180 degree. So out of this we are going to prefer the 2 by pi, which is 72 degree. In single phase voltage source inverter bridge inverter, the load current is I0 is equal to 200 sine of omega t minus 45 milliampere. The DC supply voltage is 220 volts. What is the power drawn from the supply? See here, a single phase voltage source inverter, the load current they have given and the DC supply voltage is 220 volts. So what is the power drawn from the supply? See, for a voltage source inverter, I have already told you the output voltage is independent of the supply voltage. So the output voltage is independent of the load elements. Or the output current is going to depend upon the load. So output voltage is equal to, we are going to get sigma n is equal to 1 comma 3 comma 5 up to infinity 4 into VDC by n pi sin n omega t. So here you can see clearly the fundamental component current is going to present. So only the fundamental component is present, and in the voltage you have to take only the fundamental component. The fundamental component of the voltage is equal to 4 Vs by the RMS value of the fundamental component of the output voltage is 4 Vs by pi root 2 into the RMS value of this output current, which is squared by root 2 into power factor cos of 45. So if you solve this one, we are going to get 19.8 watts, because only the fundamental component is responsible for the amount of power absorption of the load. So therefore, the power drawn or the power absorbed by the load is equal to V0 I0 cos phi. V0 is the RMS value of the fundamental component and I0 is the RMS value of this component, because both are of the only fundamental. If it is omega, there has to be omega only. That is called the fundamental component. So cos phi. Phi is the angle between the fundamental component of the output voltage and the fundamental component of the output current. So here in the voltage source with inverter, V0 is equal to, I have already told you, which is sigma n is equal to 135 up to infinity 4 Vs by n pi into sin n omega t. We have to take the RMS value of the fundamental component, which is 4 Vs by pi into root 2. So RMS value of the fundamental component of the output voltage into RMS value of the current into cos of angle between these two things. So if you solve this one, we are going to get 19.8 watt, because in the current there is only fundamental component. In the output voltage also we have to take on the fundamental component. Then only these two components are going to give you amount of power loss. An SCR is rated for 650 volt PIV. An SCR is rated for 650 volt peak inverse voltage. What is the voltage for which the device can be operated if the voltage safety factor is 2? See, listen carefully. An SCR is rated for 650 volt PIV. What is the voltage for which the device can be operated if the voltage safety factor is 2? So peak inverse voltage is equal to, 2 into Vm. See, peak inverse voltage is equal to, here simply we have to take like this, maximum voltage into see, maximum voltage into voltage safety factor. So peak inverse voltage is equal to maximum voltage into voltage safety factor. So Vm into voltage safety factor is 2, so 2 into Vm is equal to, so they have already given the peak inverse voltage is 650. So therefore, but Vrms is equal to, Vm by root 2. So Vm is equal to, so therefore you are going to get Vm is equal to 650 by 2. But already I told you Vrms is equal to Vm by root 2. So in place of Vm, so Vrms is equal to Vm by root 2. In place of Vm substitute here, we are going to get 230 volts. So simply we can say that here, this is called as RMS voltage. So here an SCR is rated for 650 volt PIV. So this is the 650 volt PIV. So what is the voltage for which the device can be operated? Means here we have to take the RMS value. So therefore, simply we can say that PIV is equal to voltage safety factor into Vm. So whereas Vrms is equal to Vm by root 2. So therefore, here we are going to find what is the value of the Vrms. So therefore, this is the voltage up to which we are going to operate it safely. This is the voltage. So therefore, this is the voltage up to which we are going to operate it safely. In PWM inverter, the effect of blanking time on output voltage is that there will be a higher order time ordinance in output voltage. I have already told you in a PWM inverter, Lagging time means for small amount of time the output voltage is zero. So because of that, a lot amount of harmonics are going to present in the output voltage. For an SCR, the gate cathode characteristics has a straight line slope of 140. For triggering source voltage of 220 volt and an allowable gate power dissipation of 0.5 watt, what is the gate source resistance? So in the question they are given, for an SCR, the gate cathode characteristics has a straight line slope of 140. So straight slope means is a Vg by Ig is equal to 140. So it is a ratio of Vg by Ig. It is called as a slope, which is 140. They have given first equation. And for triggering source voltage of Vs, Vs is equal to or Vg is equal to, here they have given, so basically they have given a Vs is equal to 20 volt. And allowable gate power dissipation of 0.5 watt means Vg into Ig is equal to 0.5. What is the gate source resistance? RS we need to figure out. So if you solve these two equations, then we are going to get Vg is equal to 8.36 volt and Ig is equal to 15.7 milliampere. But Es is equal to Vg plus Ig into Rs. So by using this equation, they have given the supply voltage is equal to 20 volts. By this we can get the value of the source resistance. Rs is equal to 195 ohm. So therefore, gate power dissipation is Vg into Ig, and the straight line slope is nothing but the gate characteristics as a straight line slope of Vg by Ig. In respect to power transistor used in inverter, the current gain will be maximum at maximum load current. Also, its collector emitter voltage, collector current, and power dissipation are maximum. In respect to power transistor used in inverter, the current gain will be maximum at maximum load current. Also, its collector emitter voltage, collector current, and power dissipation are maximum. In respect to power transistor used in power transistor used in inverter, the current gain will be maximum at maximum load current. Also, its collector emitter voltage, collector current, and the power dissipation are maximum. So we can say that in respect to power transistor used in inverter, the current gain will be maximum at maximum load current. So at maximum load current, the current gain will be also maximum. Also, its collector emitter voltage, collector current, and the power dissipation are maximum. And in conduction mode, there is no effect of gate current on the anode current of ACR. ACR in conduction mode, there is no effect of gate current on the anode current of ACR. ACR in conduction mode, there is no effect of gate current on the anode current of ACR because ACR is a semi-control device. After the ACR is on, there is no control of the gate current on the ACR. So once the ACR is turned on, there is no need to give the gate supply. We can remove it. So ACR is in conduction mode, there is no effect of gate current on the anode current of ACR. In a power circuit of 3 kV, 4 thyristors each of rating 800 volts are connected in series. What is the percentage series operating factor? It is also called as a derating factor. So in a power circuit of 3 kV, 4 thyristors each of rating 800 volts are connected in series. What is the percentage of series operating factor, or it is also called as derating factor, which is 1 minus string efficiency. So 1 minus string efficiency means overall voltage, which is 3000 by number of series connected thyristors, which is 4 into voltage rating of each thyristor 800. So if you solve this one, we are going to get 0.0625. But if we want the percentage, which is 6.25, this is called as the operating factor, or it is also called as the derating factor. So series operating factor is also called as the derating factor. So derating factor is equal to 1 minus string efficiency. So derating factor is equal to 1 minus string efficiency. So in series combination of thyristors, we can say, suppose as an example, in series combination of thyristors, suppose they are given the derating factor is equal to 0.14 is equal to 1 minus, which is 7.5 into kV, which is nothing but 7.5 into 1000 by number of series connected thyristors into 500. Means in this question they are given that the derating factor is equal to 0.14 and the overall voltage rating of 7.5 kV and the voltage rating of each thyristor is 500. So with the help of this equation, we are going to get number of ACRs required for a series combination, which is N is equal to 18. Suppose in parallel combination of thyristors, we have to go for the current rating, which is they are given again with the same factor, which is 0.14 is equal to 1 minus. Now overall current rating is again 7.5 into 1000 by N into 75. Plus again 7.5 kilo ampere by N into 75. So N means number of parallel combination of thyristors are required, where again 75 is the current rating of each thyristor. So therefore with the help of this equation, we are going to get N is equal to 16. So Now 18 thyristors we need to connect in series with a, like that we need a parallel branch of 16. So therefore total ACRs are nothing but 18 into 16. This way number of ACRs are going to get present. In parallel means we have to go for the current rating. In series means we have to go for the voltage rating. In half control bridge converter, the average output voltage is equal to, in half control bridge converter. Half control means it is a semi-control. So half control bridge converter means we are going to get a semi-control bridge. It is called as half control bridge converter means it is a semi-control bridge converter. So semi-control bridge converter. So bridge means here basically, bridge means we are going to get here a full wave we are going to get with the help of bridge. So we can't get a half wave with a bridge. So therefore it is a half control bridge converter means it is a semi-control bridge converter, because with the help of bridge we can get only full cycles. So it is a half control means it is semi-converter. Means some of them thyristors are going to use and some are diodes are going to use. So the average output voltage is equal to Vm by pi into 1 plus cos alpha. So for a single phase AC to DC control rectifier to operate in regenerative mode, which of the following conditions should be satisfied? For a single phase AC to DC control rectifier to operate in regenerative mode, which of the following conditions should be satisfied? Fully controlled bridge means alpha greater than 90, source EMF in load. So we can say that if you want to operate in regenerative mode or inverter mode, then definitely the full bridge converter, the firing angle should be greater than 90, and in the load there should be some source EMF. For a step down DC chopper operating with discontinuous load current, the expression of the load voltage is equal to. See, for a step down DC chopper operating with discontinuous load current, the expression of the load voltage. See, I have already told you whether it is a discontinuous conduction or whether it is a continuous conduction. Then we can say that here simply, see, for continuous conduction, V naught average is equal to, see, for continuous conduction, V naught average is equal to D into VDC. Whereas for discontinuous conduction, the average value of the output voltage is equal to D into Vs by beta. In the step down DC chopper, output load voltage V naught is equal to K into VDC, where K is called the duty ratio of chopper. Actually, this is a continuous load current. Then only this is the expression. Otherwise, we are going to get D by beta into VDC or D into VDC by beta. In a single pulse modulation of PWM inverters, the pulse width is 120 degree. So in a single pulse width modulation of PWM inverters, the pulse width is 120 degree. For an input voltage of 220 volts DC, what is the RMS value of the fundamental component of the output voltage? So we have to find what is the, so they have given a pulse width. In a single pulse width modulation of PWM inverters, the pulse width is 120 degree. For an input voltage of 220 volt DC, what is the RMS value of the fundamental component of the output voltage? So pulse width means 2D is equal to 120, so D is equal to 60 degree. So we have to find what is the RMS value of the fundamental component of the output voltage. So output voltage expression is equal to general expression N into sigma, capital N into sigma N is equal to small m is equal to 135 to infinity 4 into capital Vs by N pi into sin N gamma into sin N V by capital N into sin N omega t. So here capital N is equal to 1 and gamma is equal to pi by 2. So if you substitute here, we are going to get an expression. In the expression, take the peak value by root 2. So we are going to get this value, which is 171.5 volt. So therefore, the output voltage of a general expression, which is equal to output voltage is equal to sigma n is capital into sigma n is small m is equal to 135 to infinity 4 into Vs by N pi into sin N. See, sin N gamma, sin N small n into gamma, sin of small n into D by capital N into sin of N omega naught t. Maximum value of active power and reactive power demand will not change when a full load wave fully controlled converter is modified as a full wave off control converter. So we can say that the maximum value of active power and the reactive power demand will not change when a full load fully wave control converter is modified as a full wave off control converter. See, suppose if you are going to keep a load with a fully controlled converter, then if you replace the full wave control rectifier by the semi-converter, the demand of the load, the active power demand of the load and the reactive power demand of the load will not change. The maximum value of the active power and the reactive power demand will not change when a full control rectifier is modified as a full wave or like a semi-converter. So suppose there is a circuit like this. So this is like a fixed supply voltage, or you can say it is a AC source of Vs. So here we are going, it is a Vs. So it is basically here simply we can say that here, so VS is nothing but this is a AC supply. So here we are going to use two types of thyristors like triac, and here we are going to keep a load or a load, and this is a plus or minus V naught. The Z is equal to R plus JXL. So Z is equal to R plus JXL. If you write in terms of polar format, under root over R square plus XL square at an angle of tan inverse of XL by R. So here the phase angle of the load is phi is equal to tan inverse of XL by R. This is the phase angle of the load. Then V naught is controllable. V naught is controllable when alpha is lies between phi to 180. So V naught is controllable when alpha is lies between phi to 180, and V naught is uncontrollable if the alpha is lies between 0 to 5. So we can say that the phase angle of the load is equal to tan inverse of XL by R. So if the firing angle of this triac, if it lies between phi to, if it is lies between 0 to 5, means it is uncontrollable. If it is lies from phi to 180, then it is controllable. So output voltage can be uncontrollable when the firing angle lies between 0 to 5, and is controllable when it lies between the phi to 180 degree. Say suppose this is the DC motor. DC motor we can replace by RLE load, armature resistance, small amount of inductance, and a back EMF. So the motor is going to get rotate with the help of supply. Then what is the back EMF? Back EMF is equal to K into phi into L. This is a very basic relation. So EB is equal to KB into L, or simply we can say back EMF is equal to basic formula P phi N by 60 into Z by A. So simply we can write in terms of EB is equal to K into phi into L, or simply we can write EB is equal to KB into some L. KB is some constant. Suppose this is some output current you are going to see, which is from 0 to alpha it is 0. From alpha to pi minus theta 1, it is going to have a current in this manner, but after that it is again 0. If you want to find the average value of this one, so I average is equal to 1 by 2 pi integration of alpha to pi minus theta 1. This is nothing but source voltage minus EMF across the load by R, because it is a RE load. So therefore Vm sin theta minus E by R into d theta. So if you solve this equation, we are going to get I know direct is equal to 1 by 2 pi R into 2 Vm cos theta 1 minus E of pi minus 2 theta 1, where theta 1 is the sine inverse of E by Vm, because we are going to use a RE load and supply voltage is Vm sin omega t. So because of that only, from 0 to alpha we are not going to trigger. So alpha angle, alpha triggering should be lies between theta 1 to pi minus theta 1 only. Only in this range only the current is going to possible, and in the remaining ranges the current is reverse bias, so therefore current is 0. Suppose there is a circuit like this. Here this is a AC source, so this is a AC source, and here this is a primary winding and secondary winding. So these are the dotted terminals. So here there is a diode, and this is a capacitor, and this is the load voltage plus or minus V0. Then you can see it is a isolated buck boost converter. It is basically an isolated buck boost converter. So it is basically an isolated buck boost converter. This is a buck boost converter. You can see clearly here SDL means buck converter. So SDL means it is a boost converter. So here S, here we are going to diode, and is the inductor. It is going to act like inductor. So S, here S, L, D. So this is called as a buck boost converter. So this is going to act like an inductor. So this is called as a buck boost converter. So therefore V0 is equal to, so V0 average is equal to the basic formula, which is V0 average is equal to D into Vs by 1 minus D. This formula we know, but there is a transformer ratio, this A we need to include, which is by A. So this is the A. So whereas Vs is equal to, Vs is nothing but here simply, so Vs is called as the peak value of the source. So peak value of the source is equal to root 2 into V. Here we have to take the peak value of the source. So therefore the peak value of the source is nothing but root 2 into V. Root 2 into V, because V is the RMS value. So peak value is equal to root 2 into V. So therefore here PFBV is called as the peak forward blocking voltage of the switch. The peak forward blocking voltage of the switch is equal to, which is Vs plus V0 by A. So Vs plus V0 by A is called as the peak forward blocking voltage of the switch. The peak forward blocking voltage of the switch is equal to, the peak forward voltage of the switch is equal to, so here the peak value is Vs. So peak value is something but here, see here the peak value is Vs. Here the value is V0 by A. So just you have to do the subtraction. We are going to get Vs plus V0 by A. So Vs is called as the maximum value of the source voltage, and V0 by A is the voltage across this one. So therefore Vs plus V0 by A is called as a peak forward blocking voltage of the switch. Vs by V0 by A. Vs is called as the maximum value of the source voltage. Maximum value of the source voltage, which is root 2 into B. This is V naught by A, which is V naught is equal to A into D into Vs by 1 minus D, where A is the transformer ratio. A chopper operated on TRC control mode. A chopper operated on TRC control mode, you need to listen this one, whereas V naught is equal to D into Vs. So, a chopper controlled on TRC control mode means V naught is equal to D into Vs. So, D is called as the duty ratio, which is T on by T, as T is equal to T on plus T off. So, T on is called as the conduction period of thyristor. So, conduction period of thyristor means T on. So, T on means it is simply conduction period of thyristor means the time for which the thyristor is conducting, the time for which the switch or the thyristor is conducting, that is called as a T on. Whereas T off means blocking period of thyristor. Blocking period of thyristor means simply we can say that it is off. So, means simply blocking period of thyristor means the switch or the thyristor is turned off. So, therefore, T on means the conduction period of thyristor means the time for which the thyristor is conducting, because it is a step down chopper, so SDL. So therefore, the conduction period of thyristor means the time for which the switch is on, and T off means blocking period of thyristor means the time for which the switch is off. That is the meaning of this one. So conduction period of thyristor means the time for which the switch is on, and the blocking period of thyristor means the time for which the switch is off. So T on and T off. Phase control rectifier, AC voltage controller, step down cycloconverter. All these uses natural commutation method for turning of thyristors. Phase control rectifier, AC voltage controller, and step down cycloconverter. All these uses natural commutation method for turning of thyristors, because all these are going to have the input as AC source. That is the reason we are going to use the natural commutation for turning of the thyristors. So phase control rectifiers, AC voltage controller, and the step down cycloconverter, all these things are going to use the natural commutation for turning of thyristors, whereas the choppers, inverters, and the step-up cycloconverters, all these uses force the commutation to turning of the thyristors. So choppers and inverters, they need the fully controlled devices and also stepped-up cycloconverter. So in these three applications, we are going to use the force the commutation to turn off thyristors, because in these applications we need to use the fully controlled switches. Whereas in the phase control rectifiers and also in the step down cycloconverter, see, only in the two applications, phase control rectifier and step down cycloconverter only, we are going to use the natural commutation for turning of the thyristors, because the input is a AC supply. Similarly, the choppers, inverters, and the step up cycloconverter, in all this we are going to use the force the commutation for turning of the thyristors. So this AC voltage controller is no need to keep here. So this point is not there. Only phase control rectifier and the step down cycloconverter only we are going to use a natural commutation for turning of thyristors, whereas the choppers, inverters, and the step up cycloconverters, we are going to use the force commutation method to turning of the thyristors. Some important points regarding the power MOSFETs. These are constructed as to avoid punch through. In this, the channel length is relatively small and channel width is relatively large. The width is large but the length is small. The width is very large but the length is very small. These do not experience any minority carrier storage, only they have the majority carriers. These can be put in parallel to handle large currents, because these are the positive temperature coefficient devices for resistance, so we can go for the parallel operation. So we can say that these are constructed to avoid the punch through, and also here we can say that we can simply say it is a voltage control device, and here the length is very small but the width is very large, and these are the only majority carrier device but not minority carrier device. So minority carrier devices are also fully absent, because it's a positive temperature coefficient device we can use for parallel operation. So some important points of the power diodes. The breakdown voltage is not directly proportional to the doping density of the drift region. Losses in the diode are more due to conductivity modulation of the drift region in the on state. The vertically oriented structure supports large blocking voltages. So the vertically oriented structure supports large blocking voltages. Breakdown voltage is not directly proportional to the doping density of the drift region, and the losses in the diodes are more due to conductivity modulation of the drift region in the on state, and the vertically oriented structure supports large blocking voltages. So these are some of the important points of the diodes. So we can say that the breakdown voltage is not directly proportional to the doping density of the drift region. Losses in the diodes are more due to conductivity modulation of the drift region in the on state, and vertically oriented structure supports the large blocking voltages. So these are some of the important points of the power diodes. So we can say that the breakdown voltage is not directly proportional to the doping density of the drift region, whereas the losses in the diode are more due to conductivity modulation of the drift region in the on state, and the vertically oriented structure supports the large blocking voltages. So we can simply say that the vertically oriented structure is going to support the large blocking voltages. The vertically oriented structures are going to support the large blocking voltages. And the losses in the diode are more due to conductivity modulation of the drift region in the on state. Due to conductivity modulation of the drift region in the on state, the losses in the diodes are very higher. The breakdown voltage is not directly proportional to the doping density of the drift region. Single phase SCR based AC regulator. A single phase SCR based AC regulator is feeding power to a load consisting of R and L. The input supply is V and F. The maximum firing angle at which the voltage across the device becomes zero all throughout, and the RMS value of the current through SCR under this operating condition. So we have to find here a single phase SCR based AC regulator. A single phase SCR based AC regulator is feeding power to a load consisting of R and L. The input supply is V and F. The maximum firing angle at which the voltage across the device becomes zero all throughout, and the RMS value of the current through SCR under this operating condition. So at what power factor angle the voltage across the device is going to become zero for all the time, which is tan inverse of omega L by R, which is the phase angle of the load. So therefore, this is the maximum firing angle, which is equal to the phase angle of the load, for which we are going to get the voltage across the device becomes zero for all throughout. And if you want to find what is the RMS value of the thyristor current, which is equal to Vm by 2 into mod Z. So Vm is nothing but peak value, which is root 2 into V by 2 into mod Z, which is under root over R square plus omega N whole square. So Vm by 2 into mod Z. So Vm is nothing but root 2 into V by 2 into mod Z, which is under root over R square plus omega N whole square. So the RMS value of the thyristor current is equal to Vm by 2 into mod Z. So Vm by 2 into mod Z. So the maximum firing angle of the thyristor is equal to the phase angle of the load, at which we can say that the voltage across the device becomes zero all throughout, and the RMS value of the thyristor current at this condition is equal to, which is equal to Vm by 2 into mod Z. So now we are going to discuss the sinusoidal PWM. This is called as a single phase half bridge voltage source inverter. This is VDC by 2, VDC by 2. This is switch S1, switch S2. This is the RL load, plus or minus V0. So here, see, I want to find what is this is the output voltage peak value, the fundamental peak value. See, the fundamental peak value of the output voltage is equal to M into VDC by 2. So M into the supply voltage is VDC by 2. So therefore M into VDC by 2. This is the thing that you need to remember. So M into supply voltage, the supply voltage is VDC by 2. So therefore here V01 peak is equal to M into VDC by 2, which is called as the peak value of the fundamental component of the output voltage, which is M into VDC by 2. So if you want to find what is the RMS value of the fundamental component of the output voltage, which is peak value by root 2, so we are going to get M into VDC by 2 into root 2. So this is called as the RMS value of the fundamental component of the output voltage. So if you want to find how much amount of power absorbed, if you want to find how much amount of fundamental power absorbed by the load, which is equal to RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into cos of phi 1. So therefore we can say that I01 RMS is again equal to V01 RMS by mod of Z. So therefore simply we can say that mod of Z1 or mod of Z1. Therefore we are going to get V01 RMS whole square by mod of Z1 into cos phi 1. So we can see clearly Zn is equal to under root over R square plus N omega N whole square. Z1 means keep here N is equal to 1. We are going to get this value. And similarly phi 1, whereas phi N is equal to tan inverse of N omega L by R. We want phi 1, so keep here N is equal to 1. Because as it is a RL load, the current is going to lag the supply voltage. So we have to take only the fundamental component of the supply current. I have already told you the general peak value of the output voltage is equal, the general output voltage is equal to sigma N is equal to 135 up to infinity 4 into peak value is VDC by 2 by N pi into sin N omega t. Whereas the output current is equal to, simply I have already told you, as the output current is equal to simply, which is the output current is equal to, simple I have already told you, which is equal to, see, sigma N is equal to 135 up to infinity, which is 4 into peak value, which is VDC by 2 by N pi into mod of Zn sine of n omega t minus n pi by sine of n omega t minus phi n, whereas phi n is equal to tan inverse of n omega l by r. And mod of Zn is equal to under root over r square plus n omega l whole square. So therefore, we are going to get the RMS value of the fundamental output voltage whole square by mod of Z1 into cos of phi 1. So we know the value of phi 1, we know the value of mod of Z1, and we also know the value of the mod of this RMS value of the fundamental component of the output voltage. See, the expressions which I told you, when we are going to on the switch S1 for 0 to T by 2 and on the switch S2 for T by 2 to T fully. But now with the help of sinusoidal modulation, we are going to get the peak value of the fundamental component of the output voltage, which is m into the source value, which is VDC by 2, and the RMS value is peak value by root 2. So F0 is called as the fundamental output voltage. F0 is called as the fundamental output voltage, whereas F1 is called as the frequency of the reference signal. I have already told you the frequency of the reference signal is equal to the frequency of the output voltage. So F0 is equal to Fr, because the frequency of the output voltage is equal to frequency of the reference signal. So F0 is equal to Fr. So therefore, omega is equal to 2 pi F0. So if you know Fr, then you also know the F0. If you know F0, you can get the value of the omega. So you can substitute value of omega and you can get the result. This is the amount of fundamental active power consumed by this load. TS is called as a starting torque developed by motor. TS is called as a starting torque developed by motor, which is Newton meter. TL is called as a load torque, again Newton meter. TA is called as the accelerating torque, again Newton meter. Alpha is called as the acceleration, which is radians per second square, and I is called as the moment of inertia, which is kg into meter square. So therefore, accelerating torque is equal to starting torque minus load torque. So accelerating torque is equal to starting torque minus load torque. So starting torque is provided by the motor, it is generated by the motor. Here is the load torque which is required to rotate, is equal to I into alpha. So alpha is equal to d omega by dt is equal to omega 2 minus omega 1 by delta t. The amount of change in angular speed by any given amount of time. So TH is called as the starting torque developed by the motor, and DL is called as the load torque, and PA is called as the accelerating torque, and I is called as the moment of inertia, and alpha is called as the acceleration. Whereas alpha is called d omega by dt is equal to omega 2 minus omega 1 by delta t. Means in this amount of change we are going to change the angular speed. So TH is called as a starting torque developed by the motor, which is Newton meter, and TL is called as a load torque, which is Newton meter, and TA is called as the accelerating torque, which is Newton meter, and alpha is called as the acceleration, which is radians per second square, whereas the I is called as the moment of inertia, which is kg into meter square. So accelerating torque is equal to starting torque minus load torque is equal to I into alpha. So alpha is equal to d omega by dt is equal to omega 2 minus omega 1 by delta t. Means there is a change of angular speed in this amount of small time delta t. So these are some of the important formulas which are very much useful to solve any questions in the power electronics. And if you like the content of the channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, a direct reference comes to mobile. If any information needed in our video lectures, then please do comment in the comment section. We will definitely include all those information in the coming lectures. Thank you so much for watching this lecture. Please smile and take care, and bye bye.